One of the reasons that we might want to change the base of an exponential expression is because we want to find an equivalent interest rate if the interest were compounded continuously. We might do this to compare the rates for loans, or we might do this in order to just describe a loan in different ways that are easier to work with mathematically. So for this example, suppose we take out a loan with 6.5% interest compounded quarterly. Right? Then our principal at time t is however much the loan was times 1 plus 0.065 divided by, quarterly means 4 times a year, so n is 4, to the 4t. We want to get an equivalent interest rate if it were compounded continuously. So we want to turn this into something of the form P0 e to the RT. Examining these expressions, we want the base for the power t to be equal. We want to find the interest rate r so that e to the r equals 1 plus 0.065 over 4 to the 4th. So then r is going to be the natural log of, well, that expression. 1 plus 0.065 over 4 to the 4th. And again, we could use the log of a power rule to pull that 4 out, or we could just plug this into our calculator as we see it. Since 4 is not too bad, I'm just going to throw it in as we see it. So we'll have natural log of, parentheses, 1 plus 0.065 over 4, close parentheses, to the power 4, close parentheses to end the log, and we get that, okay, we want to answer as a percent rounded to 2 decimal places, so we're going to start by rounding this to 4 decimal places. R is about 0.0645, we'll round up, which is 6.45%. That's a little bit lower than when the interest rate was cited compounded quarterly. That makes sense, right? If we keep this interest rate the same and compound more often, we get more interest. So if we want to write an equivalent where we'll compound more often, the effective interest rate will be lower. So 6.5% compounded quarterly is equivalent to 6.45% compounded continuously. And what do we mean when we say they're equivalent? We mean that after the same number of years, they give the same amount of interest. We can also go in the other direction and find what the interest rate would be compounded at some frequency. And almost always we're just going to choose the interest rate compounded annually, but we could do this for any frequency with a little bit more algebra. Suppose we take out a loan at 8.2% interest compounded continuously. Then our principal at time t will be our starting loan times e to the 0.082 t. And we want to find the interest rate so that that's equal to our starting value times 1 plus the interest rate over 1 to the 1t. Right? Compounded annually means n equals 1. Okay, well, then we want to find the value of r so that the bases of our exponentials here are equal. So 1 plus r equals e to the 0.082. Okay, I feel like that's much easier algebra, isn't it? Because we just have to subtract 1 from both sides. None of this log business. We're not looking for a number that's in an exponent, so we aren't going to need a log here. We'll get r is e to the 0.082 minus 1. Another job for the calculator. E to the 0.082 minus 1 gives us, I want a percent rounded to 2 decimal places, so I'm going to round to 4 decimal places here. 0.085, and we round up. 0.0855 is 8.55%. The given interest rate is equivalent to 8.55% compounded annually.